Open up your workbooks to page 72, and let's get started on our warm-up today, practice problem number 2. Your goal here, or your task here, is to calculate the distance between each sets of coordinates below. Remember the two strategies that we've utilized, one of which, if you're stuck, you can plot the coordinates on the coordinate plane and create right triangles out of the distance you see, and utilize those right triangles and the legs and input those side lengths that you can count out for A and B to then find side C using Pythagorean theorem, which would be the distance between each point. So that was one of our strategies. A second strategy that we talked about was calculating the difference between your X values and then calculating the difference between your Y values. And those would then be related to the legs of the right triangles that you would input to a squared plus b squared equals c squared, and then again calculate for c, which would be the actual distance between each segment. So at this time, go ahead and pause the video, attempt these 3 problems on your own using either one of those 2 strategies, and then when you're done, you can go ahead and check your work with me. All right, let's go ahead and take a look at what we have done and make sure that we have the same units measurement for each distance. So if we take a look at example 1, when m is at 0, negative 11 and p is at 0, 2, for this particular one, I notice that my x values are the same, so I don't have to go ahead and graph it. I can just find the difference between my y values. So I'm going to go ahead and do that. So if I do negative 11 minus 2, that change gives me a difference of negative 13. And I know that distances cannot be negative, so I have to take the absolute value, which would give me a distance of 13 units. So the length of segment MP is 13 units long. When I look at number 2, I notice that neither my x's nor my y's are the same, so I can't just go right into that strategy and be done. I have to think about one of the other strategies, whether I'd like to plot them and create a right triangle out of them, or use the change in the 2 and then apply Pythagorean theorem. So why don't we go ahead for problem 2, let's plot them and see if your work or your answer matches mine. So if I go ahead and plot A at the origin, 0, 0, and B, so there's point A, at negative 3, negative 4, so left 3, down 4. Okay, I can see that this is clearly on a slant, so I can't count it out, so I'm going to go ahead and create a right triangle from this slanted line to then count out and utilize Pythagorean theorem. So the shorter leg is 3 units long, and the longer leg is 4 units long. So my work for problem 2 is going to be 3 squared plus 4 squared equals c squared. I know when I do 3 squared, I get 9. 4 squared, I get 16. Okay, when I add 9 and 16, I get 25 to equal c squared. Then I know that the distance cannot be 25 because first I have to take the square root of it, and I get side C being a perfect square, which is 5 units long. So no matter what method you did for problem 2, hopefully you got 5 units. If not, go ahead and pause the video here, copy down the correct work, and adjust your notes accordingly. All right, let's try a different strategy for problem 3. We could plot it just like I did with problem 2. But I'm going to go ahead and find the change in each of my x's and y's. So again, I can't use the same strategy as strategy 1 because I notice 8 and 0 for my x's are different, and 0 and negative 6 for my y's are different. So I'm going to go ahead and first find the change in my x's. So that would be 8 minus 0, which is 8. And 8 is positive, so I don't have to worry about taking the absolute value. So that's a positive distance of 8 units for one of the legs of the right triangle. And then I'm going to go ahead and calculate the distance in y. So I'm going from 0, and the change is from 0 and take away negative 6. Remember, whenever I subtract a negative, that's the same as saying 0 plus 6, so that is a change of 6 units. And again, it's positive, so I don't have to worry about absolute value there. So I know the two legs of the right triangle would be 8 and 6. So I can now take them and input them into Pythagorean's theorem. So I have 6 squared plus 8 squared equals c squared. And then I'm going to continue on, and I get 36 here plus 64 equals c squared. Oops, sorry about that. Fix that. Equals c squared. Go ahead and add 36 plus 64, and you should get 100. And then you're going to go ahead and take the square root of 100 to get the actual side length. Again, it's nice and perfect, so that would mean our side length for number 3 is 10 units long, or the distance from C to D is 10 units in length. So make sure that your work is correct for problem number 3, and if not at this time, go ahead and pause, adjust your work accordingly in your workbook. Once you are done with that, we are ready to go on to the first part of today's lesson, which is going to be lesson 12. We are moving on to a new learning target today. We are going to understand how cube roots relate to volume and edge length of cubes. So we have focused a ton on square roots so far, so we're going to take a look at what is a cube root and how it differs from a square root, and even some similarities and some of our similar strategies we can apply from square roots to cube roots. Excuse me. When walking out the door today, you should be able to know what a cube root is. You should understand the meaning of expressions like the cube root of 5, that's how we read that, and we will be able to approximate cube roots. All right, for our mathematical practices, we are going to model with mathematics using cube roots. We are going to construct viable arguments and critique the reasoning of others through a sort activity later on, and look for and make use of structure with our cube roots and comparing them to square roots. So quite a bit going on here today. All right, please join me on page 74 of your workbooks. And we are going to take a look at the first activity, which is called ordering squares and cubes. So your task here is to take these 6 problems and order them from least to greatest. Before ordering them from least to greatest, you have to think about what does each value actually represent numerically. So what is A? What is B? What is C? What is D? What is E? And what is F? And that way then, once you've gotten solutions for each of them, or approximate solutions for each of them, you can order them from least to greatest. So at this time, I'd like you to pause the video and attempt to calculate A through F on your own, and attempt to order them what you feel is from least to greatest. And if you're stuck, then you can go ahead, press play, resume, and check your work with mine. Either way, when you're done, check with me. All right, so let's take a look at the first example. A squared equals 9. This one you should be very familiar with. We are going to take the square root, right, in order to undo our squared sign on both sides of the equation. So they cancel out on the left, and I am left with the square root of 9, which I know is a perfect square. So A is exactly 3. So hopefully you got that. For the first one, again, a very familiar problem. Now, B is slightly different because instead of B being squared, we have B cubed, or B to the 3rd power equals 8. Similar strategy, though, that we want to apply with our squares. We know in the previous example that A is 3 because 3 times 3 equals 9. And we know squaring means take the number and doubling it. So if squaring means to take that same number repeatedly and double it, then cubing must mean take the same number repeatedly but multiply it 3 times as opposed to 2 times. So I'm now going to ask myself, what number can I multiply by itself 3 times in a row to get to 8? Well, if I try 1 times 1 times 1, I know that's just going to give me an outcome of 1. But let's try B being 2. What if I try 2 times 2 times 2? Does that give me an output of 8? Well, I know 2 times 2 is 4, and 4 times 2 gives me 8. So therefore, b must be 2. Another way of looking at this is in terms of cube roots. So in the previous example, we did the square root of a because it was being squared. So what I can do is, to undo a cubed sign, is something called the cube root. So I'm taking the cube root of 8, which is literally 2. And again, it's 2 because when I multiply 2 times 2 times 2, 3 times in a row, I get to 8. So now we're seeing that cubing a number has an inverse of cube rooting, just as squaring a number has the inverse of square rooting. Trying problem C now. Back to square rooting. So we're very familiar, hopefully, with our square rooting. And I know to square root because, again, C is being squared, so I have to do that inverse. So what number times itself is going to get us to 10? Well, we know that one's not perfect. So that's where we have to think about our our perfect squares that surround the square root of 10. So if I take the square root of 9, right? I know that's 3, but 10 is bigger than 9, so then I have to go 1 up. And I have to think about the square root of 16, which is 4. So this is going to fall between 3 and 4, right? Because the square root of 10 falls between the square root of 9 and the square root of 16. Okay, the square root of 10 is clearly closer to 9, the square root of 9. So I am going to approximate example C a little bit closer to 3 as opposed to 4. So maybe around 3.2 would be a good approximation. Okay, so hopefully you've got something very close to mine. If it's not exactly 3.2, as long as it's close to that, we should be good. All right, let's go ahead and look at D now. So D is going back to that other concept from above, like example B, where now we're not square rooting, but we're thinking about cube rooting, or what number times itself 3 times will get us to 9. Well, we know 2 times 2 times 2 from earlier is 8. So 9 is clearly bigger than 8. We're going to have to try something larger. So let's try 3 times 3 times 3. Well, when I do 3 times 3, I get 9, but it's the cube, so I have to multiply by that third 3. So 9 times 3 actually gets us all the way up to 27. So we know, if we're thinking about cube rooting 9, the cube root of 9 has to be somewhere between 8 and 27. So the cube root of 9 is a lot closer to the cube root of 8 than it is to the cube root of 7. So again, if I'm thinking about it in terms of in the middle here, here's cube root of 8. Okay. Cube root of 9 would be in the middle. Okay, and the cube root of 27, okay, would be over here because we know the cube root of 8 from above is 2, and the cube root of 27 we just learned is 3. Okay, so the cube root of 9 has to be somewhere between the integers 2 and 3. 9 is much closer to 8 than it is to 27, so I'm going to approximate it maybe like 2.1. So that would tell me D is approximately 2.1. All right, so let's take a look at E. E is another squared problem, or to do the inverse of your square rooting. So this one should be familiar again to us. We're taking the square root of both sides. So we can undo that square on the left, and on the right, the square root of 8 again is not perfect. But we can think about our perfect squares that surround the square root of 8 as our approximating strategy. So we know the 3 times 3 is 9, and 2 times 2 is 4. So the square root of 4, and the square root of 9, and the square root of 8 falls in between it. So that's between 2 and 4. 8 is definitely closer to 9, so we're going to approximate that closer to 4. So oh, I'm sorry, not 4, that was a mistake. The square root of 9 is 3. So we're going to approximate our decimal closer to 3 than 2. So maybe something around 2.8, 2.9, somewhere in that vicinity for E. So maybe around 2.8. And then finally, our last example, f cubed equals 7. So this is going to our new concept of cubing numbers. So what number being multiplied by itself 3 times is going to get us to 7. So now we're doing the inverse of cubing, which we are learning is called cube rooting. Okay, so then those can cancel out on the left. And I have to think about what 3 numbers can I multiply by themselves to get to 7. Well, it's an imperfect cube, right? Because I know 2 times 2 times 2 from earlier gets us to 8. And the cube root of 8 is larger than the cube root of 7. So then I'm going to think about 1 smaller than 2, which is 1. So that would be 1 times 1 times 1, or the cube root of 1. So when I do the cube root of 1, I know that is 1. When we do the cube root of 8, we learned from earlier, that is 2. So therefore, the cube root of 7 must fall somewhere between 1 and 2. 7 is a lot closer to 8 than it is to 1, so I'm going to approximate my decimal closer to 2. So maybe around 1.8, 1.9-ish, somewhere in that vicinity to approximate our example for letter F. All right, so at this time, check to see if your work matches mine, and if not, you need to add to your notes. Pause the video, add to your notes now, and then we can go ahead and order them based on our approximations here from least to greatest. So if I am looking, I am noticing that F is the smallest out of the 6, 1.9. So I'm going to list F first. Then I'm going to continue looking, and then I see that B is the next smallest at 2, hiding in my work over here at 2. And then after B, I notice that D comes in at 2.1, approximately. And then after D, I'm noticing that example E would be next at approximately 2.8. Oops, I want the letter, not the numerical equivalency. And then finally, or no, not finally, we have 2 more to go. The next largest would be A at 3 units. And then finally, the largest one here would be C at approximately 3.2 units. All right, so again, make sure you have all the work appropriately done in your workbooks for each of these problems. Especially make sure you have all the steps that I have in green, or excuse me, in blue with our cube roots, because I did all the cube roots in blue today on purpose so that would all be done the same color so that stands out to you. So make sure those blue examples are really clear in your notes as well. So since this is our first time seeing the examples with cube roots. Once you're done adjusting your notes, let's go ahead and go on. Okay. An important note, since we weren't able to do this together with the class since I'm out today, but an important note to realize after doing this activity is that you previously learned that the equation c squared equals 10 has solution of c equaling the square root of 10. Similarly, we can say that the equation of d cubed equals 9 has a solution d equals the cube root of 9. So if we think about this next example, f cubed equals 7, to write out its solution, we're taking the cube root of 7. So I would go ahead and cube root both sides to undo the cubing on the left, and that's how I get f to equal the cube root of 7. And that's as exact as it's going to get because there's no perfect cube. There's no 3 numbers that I can multiply perfectly together to make 7. So that's when we'd have to do that approximation piece like we did in the last activity. Another important note to realize is while square roots are a way to write the exact value of the side length of a square with an unknown area, cube roots are a way to write the exact value of the edge of a cube with a known volume, which we will do in the next activity. So just like we can relate square roots to squares, we can relate cube roots to physical cubes. All right, so let's go ahead and take a look at this activity at the bottom of page 74 in your workbooks. It is your job to fill in the table, given the information here and what we just learned about with cube roots. Notice my little note in blue. If you're unsure of what to put for the volume equation, remember that the volume of a cube is the cube of the edge length. Or another way we can write that out is side cubed equals volume, or volume equals side cubed. I'm sorry, and I totally wrote squared. That's a big no-no, because volume we know is cubed, three-dimensional, right? All right, so this should help you guys out, hopefully. So if you could at this point, pause the video here, see if you can attempt the table on your own, fill in what you think you can, and then you can resume and check your work with mine. All right, so let's take a look at what you came up with in your table and see if it matches what I came up with. So if I look at the first entry and I have a volume of 27 cubic inches, that tells me what number for my side length do I have to multiply by itself 3 times to get to 27? Well, I know that 3 times 3 times 3 will equal 27. Or another way of showing that using our volume formula is 3 cubed equals 27, right? So that must mean my side length for my cube in this first example is 3 inches long. How would I write that out in the volume equation? Just as I did below. 3 cubed equals 27. So hopefully your first entry matches mine, and if you need to adjust, please do so. Let's take a look at the middle entry. So the second entry given to us is the cube root of 5. So that looks quite different from the first example. But what we just learned in the previous activity is if I want to undo that cube root, I can go ahead and do the inverse of cube rooting, which is cubing. So the math I'm going to do for the second entry of the cube root of 5 is actually cubing the cube root of 5, and then those two pieces cancel out, and I'm left with 5. So that tells me that if I have a side length of the cube root of 5, its volume must be 5 cubic inches. How would I write that in the volume formula? Well, that would be the cube root of 5 all cubed equals 5. So again, just as squares and square roots undo each other with our area formula, cubing and cube roots undo each other within our volume formula. So if the side length is a cube root of 5, then we undo it with cubing, and that leaves us with a volume of 5 cubic inches. Let's take a look at the last example where they give us the volume formula, and we are going to work backwards to pull out the volume and the sides. So if the cube root of 16 all cubed equals 16, then this here is my V, my volume. So our volume must be 16 cubic inches. Okay. And similarly to the last example, there is no perfect cube root for 16. So that's why we leave the side length as the cube root of 16. And that would be the most exact form of writing its side length, because there is no perfect cube root of 16 again. Okay? So if you did not get what I got for this table, please take a moment, fill it in now, and make sure that you have the correct information. Okay, we're going to skip the Are You Ready for More today. These 3 questions are not in your workbook, unfortunately, but you do have a little bit of workspace at the bottom of page 74 and the bottom of page 75. Please do not take up all the space on page 75, because you are going to do the card sort next in just a moment. So you'll need to leave some space on page 75 to write down notes and things from the card sort. But any little space at the bottom there that you can utilize. Let's practice a little bit more with cube roots and approximating. So What integers does the cube root of 55, or excuse me, the cube root of 5 fall between? Again, I know there are not three numbers that are exactly the same that I can multiply by themselves to get to 5. So I'm going to start with some small numbers and work with that. So I know the cube root of 1 is 1 times 1 times 1, right? So that'll work as a surrounding integers for the cube root of 5. And then I know that 2 times 2 times 2 is 8, right? So that 2 times 2 times 2 would be represented as the cube root of 2, okay? I'm just going to move my 8 over so it's underneath that cube root of 2. So that tells me that the cube root of 5 must fall between the cube root of 1 and the cube root of, I totally wrote that backwards, of 8, which is 2. My apologies. Let's fix that. The cube root of 8, which is 2, because 2 times 2 is 4, right? 4 times 2 is 8. And 5 falls between 1 and 8. A little bit closer to 8, so maybe around 1.6 might be a good approximation. So we could say that the cube root of 5 is approximately 1.6 units long. All right, let's try one more. What about if we wanted to try the cube root of 16? For the cube root of 16, we know we're going to go higher than 2, right? So let's try 3 times 3 times 3. So when we do 3 times 3 times 3, and even from an earlier example, we learned that 3 times 3 times 3 is 27, right? Because 3 times 3 is 9, and 9 times 3 is 27. 16 is obviously smaller than 27. But larger than 8, right, when we did our previous example of the cube root of 8. So we know that the cube root of 16 must fall between the cube root of 8 and the cube root of 27. Well, when we did the cube root of 8 earlier, we know that's 2. We just did the math above for the cube root of 27, which is 3. So we know the cube root of 16 has to fall between the integers 2 and 3. 16 it's about halfway between, so if you wanted to approximate this around 2.5, that would be okay. So the cube root of 16 is approximately 2.5 or 2.5. Okay. The third question asks you to name another volume for a cube with edge lengths between 2 and 3. So think about what other numbers besides the cube root of 16 that could be an edge length for the volume. That would fall between essentially 8 and 27 is what you're looking at. So we could list numbers like the cube root of 9, the cube root of 10, the cube root of 11, the cube root of 12, on and on and on, or even the cube root of 26. Anything that falls between the cube roots of 8 and the cube roots of 27 would give us a volume with edge lengths between 2 and 3. So as long as you have something listed in between the cube root of 8 and the cube root of 27, you are good. So all of those examples work. And that would approximate between 2 and 3. All right. At this time, please make sure everything is in your notes accurately, and you're going to go ahead and complete a sort with people in your groups or people who have finished up the first 2 activities. So you will need to ask Mrs. McNulty, you'll shut down your Chromebooks at this time and ask her for the cards. You'll have about 10 minutes to complete this sort with your partner or within your group. You cannot use a calculator for this activity. You'll be given cards to sort into sets of 3. For each card with a letter and value, find the 2 other cards that match it. One shows the location of on a number line where the value exists. The other shows an equation that the value satisfies. Also pay close attention to the notation as to not mix up the cube and square roots. So they're both intertwined in this activity like the first activity we did today. Be prepared to explain your reasoning for as far as your sort goes with the whole class. So at this time, go ahead, close down your Chromebooks, and raise your hand, and Mrs. McNulty will be over to pass out the cards for the sort and to further explain things if needed.